Hydrogenation is the addition of hydrogen across a pi bond. The reaction is typically conducted in the presence of a metal catalyst such as palladium, platinum, or nickel. Sometimes the catalyst is adsorbed onto carbon, such is the case with the common catalyst palladium on carbon. The net result of the reaction is that the alkene pi bond is ultimately reduced so that the product is an alkane. This is a reaction for which typical curved arrow mechanism is not typically drawn. However, we can still break the mechanism into three main steps. In the first step, hydrogen adsorbs onto the metal surface and dissociates or homolyzes into two hydrogen atoms. Secondly, the alkene substrate adsorbs onto the metal surface as well, and it then adds a single hydrogen. Finally, the addition of a second hydrogen to the substrate generates the product, which desorbs from the metal surface. It's very important to note that during this process, both hydrogen atoms add to the same side of the alkene substrate, which makes this a syn addition. In this specific example, a symmetrical alkene reactant is used. However, even when the alkene is unsymmetrical, regiochemistry is not an issue in hydrogenation because the same group is added to each alkene carbon. In this reaction, the alkene pi bond is reduced and the net result is an alkane product. In this particular instance, no stereocenters were formed during the reduction, so wedges and dashes need not necessarily be used when drawing the product. In other words, this representation of the product is the same as this representation of the product. However, since two carbons of the reactant are involved in this transformation, it is possible that 0, 1, or even 2 stereocenters may be formed during the reaction. Consequently, stereochemistry will sometimes be a concern. In this specific example, a single stereocenter will be formed as a result of the reduction. The alkene substrate is flat. In other words, both alkene carbons are trigonal planar in geometry, and so the hydrogenation can occur from either side. However, only one of the two new tetrahedral or sp3 hybridized centers is a stereocenter, and that is reinforced by drawing only that stereocenter using wedges and dashes. The products are the enantiomers R and S 3-methylhexane. In this specific example, though, two stereocenters will be formed as a result of the reduction. Since hydrogenation is a syn addition and the hydrogens add to the same side of the alkene substrate, only 2 of 4 possible stereoisomers are formed. And they are the syn enantiomers, in which both of the new hydrogens have added either from above the alkene substrate or from below the alkene substrate. While it is always important to be on the lookout for internal symmetry, it is especially important to do so in reactions where 2 of the same atom are added across a pi bond. For instance, this substrate is very similar to the one used on the previous slide. It simply lacks one methyl group. Syn addition of hydrogen to this alkene yields a meso-alkane product. And remember, that is a compound that has an internal plane of symmetry. As a result of that internal plane of symmetry, meso compounds are overall achiral. And so this is the sole product of the reaction. In other words, it has no enantiomer. In summary, hydrogenation adds H2 across an alkene pi bond in the presence of a metal catalyst. The stereochemistry of the addition is syn. There is no carbocation intermediate in this reaction, and therefore no rearrangement is possible. It's worth noting that there are additional catalysts that can be employed in hydrogenation reactions. For instance, Wilkinson's catalyst has this molecular formula. The triphenylphosphine ligands on the rhodium can actually be replaced with chiral non-racemic ligands to give a chiral catalyst that can be used in asymmetric hydrogenation. Asymmetric hydrogenation would produce only one of the syn enantiomers as a reaction product. It is typically not feasible to predict which particular syn enantiomer would predominate. It's usually sufficient to know that enantioselectivity is possible in such reductions. Asymmetric hydrogenation can also be performed with other metals, such as ruthenium, bearing chiral non-racemic ligands as well. The preceding has been an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, or in paperback at a discounted price from Lulu.